Yeah, all I remember is
Alright, let's get started. Can y'all hear me in the back? Does the microphone work? I can't really tell. Can you tell?
get really close to the screen.
Probably not. Didn't work, but okay. Well, if you guys can hear me in the back, we're good regardless, I suppose. Okay, how's everybody doing today? Lights every time. How do we feel about that? Better? Okay, cool. Alright. Announcements. Project Zero is due tonight, right? Good. Don't forget that. Homework 1 is coming soon, hopefully today. Project 1 will be coming soon, also hopefully this week. And it will be search-based. It's going to be much more involved than Project 0 was. So Project 0 was not indicative of the kind of project workload. Project 1 will be. Okay? So keep that in mind. Okay. So last time we wrapped up informed search and we did a bunch of examples on the board. We also related some of those concepts to some more real-life concepts in robotics. Clarifications from last time, there were a couple of really good questions. I'm still looking into those. I'm going to probably post discussions on Canvas for these specific questions, or I may just address them next time, okay? All right, so this time we're going to continue talking about search, but kind of a different kind of search, or a different kind of problem. So far, what has search been for? Well, we've kind of looked at search problems where we have some single agent moving in some abstraction of the world or operating on some abstraction of the world. It has deterministic actions. We can fully observe the state. There's a discrete state space, a discrete action space, things like this, right? So that kind of falls under the category of planning, where we want to determine some sequence of actions that takes us from some start state to some goal state, right? And the path to the goal, that's the important thing here, right? These paths may have various costs or depths depending on the abstraction, and we looked at some heuristics, right, to give problem-specific guidance to us. Now I want to talk about a different kind of search problem. This one we're going to call identification. And that's where we have some set of variables and we want to come up with some legal assignment to those variables. And so we can look at this as a search problem, but it's a little bit different. And the difference is that what we're looking for is a valid goal. The path we took to get there doesn't matter at all. Okay? In some formulations, in fact, all of the paths are going to terminate at the same depth. All the goals are going to be at the same depth of the search tree, potentially. And so we're going to talk about constraint satisfaction problems, or CSPs. And these are a specialized class of identification problems. So that's what we're going to talk about today. Okay, constraint satisfaction problems. So how are constraint satisfaction problems, or CSPs, different from standard search problems? So in the standard search problem, we have this state, right? And the state, in the state, we kind of have encoded some model of the world. We have a goal test that says, for some state, is this or is this not a goal? Right? We have a successor function that operates on states and takes you from one state, given some action to another state. Right? And if we look at this goal test, we can kind of conceptualize this goal test as this black box, right? We feed it a goal, or we feed it some state, and it says, this is not a goal. We keep looking, this is not a goal, this is not a goal, this one is a goal. Right? So it's this black box kind of judge of goalness. Right? In CSPs, these are a little different. So this is a special kind of a search problem, so conceptually they're very similar. A lot of the ways we've solved these in the past are going to apply, or concepts are going to be similar at least. But here we have states defined by some set of variables, and each variable can take on some value from a domain. And that domain may be specific to the variable, or the domain may look the same across all the variables. Right? And the goal test then is going to be, we have some set of constraints defined across variables. The goal is going to be an assignment of the variables that satisfies those constraints. Does that make sense? Okay, so this definition here is a simple example of a formal representation language. This is our first example of a formal representation language. We're going to see more of these as the semester progresses. But the idea is this is a way to write down your problem, and that allows the use of general purpose algorithms as people develop them on your problem. And this can generally be more powerful than standard search algorithms. Okay, so let's look at an example. We're going to look at map coloring. Map coloring is a pretty intuitive problem where you have some map, and you want to color each of the various zones of the map, but you want to make it easy to read, so you don't want adjacent zones to be colored the same thing, right? And so here we have a map of Australia. I believe these are states. Is that right? Australia has states as well. Okay, so these are the states of Australia, and we want to color each of these states such that no adjacent states have the same color, right? Okay, so this is called map coloring. This is an example of a CSP, but it is not the only example of a CSP. Most CSPs are not map coloring, but it's a good running example, okay? So what are our variables here? Well, let's say that our variables are the states themselves, right? So we want to assign some value to each of these variables, right? And that brings us to the domain. Let's, for this specific instance, say that we have 3 colors that we can color these variables with: red, green, and blue, right? Okay, so what are our constraints then? Adjacent regions have to have different colors, right? Now there's 2 ways to write down constraints. There's implicit and there's explicit. And so implicit is some abstract notion of the constraint, right? We say Western Australia can't equal the Northern Territory, right? That seems pretty explicit, but it's not actually explicit. This is implicit because there's some notion of equality. You have to do some check on these values, right? Maybe there's some code that has to run in order for this to be checked. This is implicit. By contrast, an explicit value would say, for the tuple WA, NT, these are the valid assignments, explicitly. It must come from this set, right? That is explicit, the other is implicit. You see the difference? Okay, cool. All right, and so then the solutions are assignments that satisfy all of the constraints. For example, the coloring that we have here, right? But not everything is map coloring, so let's look at another example. Has anybody heard of the n queens problem? Okay, who at least knows how queens work in chess? Okay, so if you don't, the queen is a specific kind of piece in chess, and it has a specific way that it threatens other pieces. So let's see if this works. Trying out some new technology today. The queen. It's not working. Hold on. All right, that's great news. The queen can go this way, right? It can go this way, it can go down, and it can go diagonal. This is harder without the word okay, so the idea here is that you have some n by n, generally n by n chess grid. You want to place n queens on it such that no queen is threatening another queen, right? You kind of want your chessboard to be peaceful in this way. Okay. So how do we formulate this? Well, we have a bunch of choices for how we can formulate this problem. One instance would be to look at the variables as each square on the chessboard, right? So then we have n squared of them, right? And each one can take on the value, has a queen, does not have a queen, right? Okay. So then what do our constraints look like? Well, if we look at them explicitly, we can say, well, we know, for instance, that every column can only have one queen, right? So that's what this is saying. This is saying if we look at two squares in one row, right? That's the I index that's shared between these two values in the tuple. For any j and k, they can either take on the value 0 queens at those two places, or one of them can have a queen but not both, right? You see that in this formulation? Okay. And then we can encode kind of the other ways that queens work and these other explicit constraints and go on from here. But that's not enough, right? Because there's some trivial value. If we don't look at that new constraint over there, we could just say there's no queens, right? And then we've satisfied this set of constraints, so this isn't enough. So we need some constraint that says there's n of them, right? Since we assign values of 0 to 1, we can always just sum over the whole board and say that has to equal n, right? Okay, so this is a formulation. This works, right? But it's maybe not the best formulation because we can actually encode some of the structure of the problem into our formulation to make these a little easier on ourselves. So, for instance, we know that each row has to have a queen, right? And we know that there have to be n queens. So let's make our variables the queen in row 1. And then the second variable will be the queen in row 2. And the third variable will be the queen in row 3. And so on, right? And then the values that those can take will be their columns. Does this make sense? Okay. And so now what do our constraints look like? Well, we have way fewer variables than we did last time, but our constraints are kind of a little more complicated, right? Well, we could just use this notion of implicit constraints. For any two queens, they can't threaten each other, right? That's fair. You could write this out explicitly, but it gets much more complicated. For instance, you could say something like this, but it'd be a lot of these. So the map coupling problem, these are kind of two examples of CSPs, right? And we use both of these moving forward. So let's talk about an abstraction that we can use to kind of encode our CSP. And we're going to use something called a constraint graph. So here, we're going to have a node in our graph for each variable. And then we're going to have an edge between two nodes if there is a constraint that operates on those two variables together. Okay? And so this is kind of a simplification of the general CSP because in the general, these constraints can operate on any number of variables. Right? One, you could have a constraint on a single variable. That functionally looks like a restriction of that variable's domain, right? That can be conceptualized as a constraint with one value, with one that operates on one variable. Binary constraints, that's what we're looking at here. They take two variables and operate on them, right? But you can have constraints that operate on 3 or 4 or however many, okay? But here, kind of in this simplification, we'll say there's an edge if there is a binary constraint between the two values, right? Okay, so in our case here, we have our states in Australia. Each one's a node, right? And if there's an edge, that's because they're adjacent and there's a constraint that says they can't be called the same thing, right? Okay, so as I mentioned, this is a subset of CSPs called binary CSP, where each constraint relates at most two variables. Okay, so general purpose CSP algorithms are going to use this graph structure. So why do we formulate this as a graph? Because a lot of very, very smart people have been working on graphs for a long, long time, right? So there's a lot of machinery in place already in computer science and mathematics and graph theory in general that we can use if we're formulating our problems as graphs, right? Okay, so for instance, we can look at, say, connected components on this graph, right? And if you have distinct connected components, those are subproblems. There's no constraints that exist between the two. You can solve them separately, right? For instance. So Tasmania, we can call it Tasmania whatever we'd like. There's no constraints going into Tasmania. It doesn't matter. That's an example here of why we're using this. Okay, here's another example. This looks a lot different. Has anybody seen Crypt Arithmetic before? Okay, so the idea is that you have these variables. Each of these has an integer value. They're different if they're a different letter. And you want to make the math work, right? And so what would our variables be here? Let's do hands. I like hands generally. Sometimes I forget, but yes.
Maybe the initials of the lands.
Well, let's talk about crypt arithmetic exactly. So we're trying to add
2 and 2 and 4.
yeah, exactly. But where each of these letters is an integer value that you don't know, right? We're trying to solve it. So what would our variables be? Yes.
The letters.
The letters, right? Yeah. So T, W, O, F, U, and R. Right, is that enough?
Probably A through Z.
You think A through, well, there's no A, right, so it doesn't really mean much if A is added, but potentially yes.
Maybe like carryovers?
Exactly. Yeah, so we need to add kind of 3 extra variables. So we have our letters here represented in the problem, and then we're going to have these carry bits. right? That's because we have to say that O plus O is equal to R, but it's not necessarily equal to R, right? It's equal to R mod 10, right? So O plus O we could say is equal to R plus 10 times either 0 or 1, right? And that's going to be this carry bit x1. Does that make sense? Okay. So what's the domain then? Yes?
A 1 through 10 value? Or 0 through 9?
Let's say 0 through 9, there's 10 of them, right? And we could say that that's true for all of them, but we could actually have a restricted domain for the x's. We could say they're 0 or 1, right? Because no two values are going to add up to something 20 or more, right? But yeah, so that's our domain, right? And then what do our constraints look like? Here's one. They all have to be different, right? All of the named variables from the problem have to be different, right? That's not a binary constraint, is it? Well, it's operating on the whole set, well, excluding the carry variables. That's different than what we've talked about so far. But you can actually turn this into a set of binary constraints if you just do pairwise inequality, right? But in general purpose CSP solvers are going to work on, most of them are going to work on constraints that have more than 2 variables, but in this class, for kind of ease of exposition, we're going to mostly talk about binary constraints. Okay, we have these other constraints, right? As I mentioned, O plus O has to equal R plus the carry bit times 10, right? That's how the math works, and so on and so on, right? Okay, and so we made a constraint graph that looks like this. So this looks very similar to what we had last time, but now we have to have this notion of edges that exist, constraints that exist between more than 2, right? So generally people will write the variables as circles in these graphs, and the constraints as squares, and the variables that the constraints operate on are going to have edges between the squares. Does that make sense? Okay. Here's another example. Sudoku. Have we talked about Sudoku yet in this class? Just a little bit. Okay, so Sudoku is an example of a CSP, right? Where the variables are going to be each open square. The domain is going to be the values 1 through 9 in this case, right? Yeah, 1 through 9. And then the constraints, you're going to have some 9-way, all different constraint for each column, the same for each row, and for each subsquare, right? This is how Sudoku works. Okay, as I mentioned, you can take these all different constraints and actually make them a big set pairwise inequality constraints if you want to. Okay, here's another example, the waltz algorithm. So this is from early computer vision work. And this is if you take some line drawing, we want some 3D realizable structure that correlates to what that line drawing looks like. That doesn't look like some Escher drawing, right? So if you look at this corner here, that consists of the 3 lines, or this cube here, that can be kind of coming out, or it can be kind of an internal corner, right? There's nothing specifying that in the drawing. And so if you have these adjacent to each other, they start to impose constraints on each other. There's 2 ways to solve this one now. You see both of them. One's more obvious, it's a cube without the corner. The other is the opposite of that, kind of the negative of that, right? You see them both kind of tricky. Right, but this is an example of a CSP that was used kind of early on in Vision. Okay, let's talk about the variety of CSPs that there are. So we have ones with discrete variables, right? And in that we can have CSPs with finite domains. If you have n variables with domain of d for each of the variables, then you have d to the n possible complete assignments, right? And so in the worst case, that's going to be our runtime generally. Okay, so this is like Boolean CSPs, and this includes Boolean satisfiability, which is one of the classic NP-complete problems, right? Generally, these are NP-complete problems. In fact, most of the problems we talk about in this class are going to be NP-hard, at least NP-complete. Some are going to be worse, like some of the motion planning problems I was talking about earlier, P-space hard, which is at least as hard as NP-hard, but we don't know if it's harder. Anyway, right? It's AI. So these are hard problems, right? Capital H, hard, right? Okay. We can have CSPs with infinite domains, right? Where the value of this variable can take on an integer, right? That's discrete but infinite, okay? These look like maybe scheduling. In the case where we have linear constraints, that's solvable. If we have nonlinear constraints, it's not decided. Okay? We can also have continuous variables, right? This is like start and end time of various things. So if your scheduling doesn't look discrete but now has continuous values, for instance, right? And if you have continuous variables and linear constraints, that is linear programming, right? Who here has heard of linear programming? Okay, so that's covered earlier on in the that's great. Okay, so with linear constraints and continuous variables, we can solve that in polynomial times using like simplex methods, etc. Right? Cool. Okay. What about the varieties of constraints? I kind of touched on this a little bit, but let's make it more formal. We can have unary constraints, right? That's this value can't take. It's a restriction on the domain of a variable, right? Okay, we can have binary constraints between two. You can have a higher order constraints involving 3 or more, right? Now, in addition to these true or false, yes or no constraints, we can have preferences, right? We say, I like red, so I would prefer as much red in my map coloring as is possible while obeying the constraints, right? And we can do this by assigning a cost to each assignment. That's frequently how we would encode this preference. And now we've blurred the lines a little more between optimization and search, right? Which is something that we've talked about a couple of times here. So we're going to ignore that until we get to base nets later in the semester. Okay? So that gives rise to constrained optimization. That's a huge branch of mathematics, obviously. So there's a lot there. Okay. What about some real-world CSPs? So these come up actually very frequently. There's a lot of important problems that can be formulated as CSPs: scheduling, timetables, circuit layout, fault diagnosis, all kinds of stuff. Okay. A lot of these problems are going to involve real value variables. Okay. So now we talk about what CSPs are. How do we solve them? Well, last week we talked about a bunch of ways to search for things, right? And what we're doing here is functionally search. So maybe we can apply some of those concepts. So can we formalize our CSPs as a standard search problem? Sure. We can have the states be defined by the values assigned, including partial assignments, right? So then our initial state would be the empty assignment, right? We have a set of variables with nothing assigned. Our successor function might assign a value to those to an unassigned variable, right? And we have a goal test. Is the current assignment both complete, as in all variables have been assigned a value, and does it satisfy the constraints? That's just search, right? This looks exactly like what we were doing last week. So we can apply some of the algorithms that we talked about last week to this, right? So we're going to start with the straightforward kind of naive approaches, and we'll improve them based on CSP-specific things, okay? So what was kind of the best uninformed search that we had last week, generally? BFS, right? That seemed to work the best. I really wish this pencil thing was working. Does anybody know how to get that to work? Is that okay? Sure. Anyway. Okay, so what's BFS going to do here? I actually do want to draw this. So okay, so let's look at BFS under this, search formalization of the CSP that we've defined. Well, how's it going to behave? So we have our start node, right? Yes. This is going to be an empty assignment, right? Nothing's assigned. Is this visible in the map? Not really. It is? Who says no? Not visible. Okay. Well. Is that better?
Yeah.
Better? Yeah. Okay. So then what are S's successors here? Well, there's going to be a bunch of them, and it's going to be an assignment to a variable, right? So maybe we assign, in this one, oh boy, WA is red, right? Right, but the rest are unassigned. Okay? And this one's going to have a bunch, that's much better, of successors right, where WA is red and then we make another assignment, right? So maybe this one looks like WA is red and NT is blue, right? Okay, this one's gonna have a bunch of children, and this one's gonna have a bunch of children, right? And on and on and on and on, right? This is gonna look just like a search tree, but it's gonna grow exponentially as we go down. So what does BFS do? Well, it's gonna start here, right? That's great. Is it a goal? No, we're not complete. So now it's gonna check everything in this row. Does that seem like a good idea? Yes.
The row's gonna be massive because you can select any color for any of the states.
It's gonna be humongous. Yeah, yes.
Yeah, and I'm assuming that also includes illegal assignments like making both WA and SA red.
Yeah, we haven't talked at all about enforcing these constraints, right? The search space doesn't say anything about that. It's gonna be enormous, right? And BFS is gonna go through this row, and then this row, and then this row, and then this row. But where are all of the solutions? They're at the bottom, right? Every single one, valid and invalid. So BFS is going to go through the whole tree, the entire tree, which is exponentially big, humongous, enormous, right? Before it even starts considering things that have complete assignments. It's not great, right? But we have a naive, uninformed search algorithm that was good at getting deep quickly, right? All of these are tree search examples in the way we formalized it, but specifically depth first search here, right? We want to get deep, we want to do it quickly. Well, we spent all of last week making fun of depth first search and how bad it was at everything, right? Maybe we need to apologize because it turns out that depth first search is going to be the structure on which we build almost all of our CSP solvers. This probably lends insight into why anybody even considers depth first search when we last week decided it was worse than almost everything. Right? Okay, so we're sorry, DSP or DFS. We apologize. We'd like to continue working with you. So how's depth first search going to work on this problem? Well, let's look at an example. Work on this technology thing, we'll have until it works next time. Okay, so let's look at an example, a video of DFS running on a very similar problem. So this is functionally equivalent. We have these states. Each one can be colored red, green, or blue. If they're adjacent, as defined by the graph structure here, they can't have the same color, right? Okay, so let's see how this works. So what we're going to do is we're going to assign a value to the first one. Right? It's going to be the first value in our domain, and we're going down the left side, right? And then we're just going to keep deepening. But how do we deepen? Well, for the next one, we're going to pick the first value in the domain as well. And that's going to look like, survey says, blue, right? Cool. Well, let's keep going. We're going to get deeper and deeper and deeper, right? So we've reached the bottom, finally. So now we can say, is this a goal, right? This is the first time that we've had any chance of it being the case that it's a goal. Well, it's completely assigned, but it doesn't satisfy the constraint, right? So what's depth first search going to do? It's going to change the last one, right? And it's going to go on. And it's going to do an exponential amount of work every time. Right? We're stopping in here because we don't have all day to watch it go. Yes?
One question. Depth first search is supposed to go through all the children first, right?
It goes through one child first. Down, 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 down.
Yes. So why did it move from the third node from the bottom right all the way to the top left node instead of...
Very good question. This is a very important distinction. This is not our search graph or search tree. This is the constraint graph, right? The edges on here don't relate at all to the edges on our search tree. The edges on our search tree represent actions, right? Action is just an assignment of a variable. You can assign any variable at any time. That just corresponds to a different child in the search tree, right? Very good question. Very important distinction, right? So functionally, we can pick an arbitrary ordering here, right? We can assign them at any time, right? And we're going to play with that concept to make this more efficient later today. Okay, but that's what depth first search does, right? Not great. Why is it not great? Because we had a problem with our second assignment, but we didn't start considering constraints until we got all the way down the tree, right? So that's one of the problems here with naive search. So we're going to talk about something called backtracking search. This is going to be an extension of depth first search. It's going to be built upon depth first search, like most of the things we talked about today, maybe all the things we talked about today, and most of the things we talked about this week. And basically, this is going to be kind of the least complicated, uninformed algorithm for solving CSPs. And we're going to add to DFS two ideas. The first is that we are only assigning one variable at a time, and some of these trees are kind of repeated work, right? Because it doesn't matter if we say Western Australia is red and the Northern Territories are then green, and then also consider first assigning the Northern Territories green and then Western Australia red, right? That doesn't matter. Those are the same thing. And we only need to consider assignments to a single variable at each step. And then we're also going to check these constraints as we go, right? So we're only going to consider values which don't conflict with our previous assignments as we start assigning, right? And so this looks like the domain of the node that we're coloring next has been restricted by our previous assignments. Does that make sense? This is kind of like an incremental goal test. Now this means we might have to do some computation in between each assignment in order to check these constraints, but we're going to have discovered that problem in the last one much earlier. Okay, so depth first search with these two improvements is called backtracking search. It's not the best name, but that's what it's called. And the idea is that as you discover violations in the constraints, you're going to backtrack of your search, make different choices according to DFS's ordering conventions, and then continue. Okay? All right. This simple algorithm can solve an n-queen problem in reasonable time in about 20 minutes. Okay. So what would that look like in our map coloring example? Well, so this one has 3 children because we fixed the ordering in which we're assigning these things, right? So then the left one, however, only has 2 children, right? Because as we look at the children of the leftmost node, we say one of our conceptual 3 children, which is assigning that second territory the value red, violates a constraint, and so we want to consider, right? And we go on from there. As we assign this third territory, red appears again, but green is now gone, right? We have red and blue. Make sense? Okay. So here's the pseudocode for this. I'm not going to go through it in detail. It's in the book. But there's some key concepts. The first is that it's implemented recursively, which is how this is frequently done. So basically the way it works is if you've assigned all of your values, you're done, right? Because we enforced the constraints in the assignment process, right? So if we just get to a full assignment, we know it's valid, right? So we're done. Great. Otherwise, we're going to select some unassigned variable with some ordering. And then for each value in the domain, if that value doesn't violate the constraints, we're going to recurse on that. If it does, we ignore it, right? Okay. So where are our decision points here? Like where are we making kind of arbitrary choices? The first is in the order in which we're assigning variables, and the second is in the order in which we're exploring the assignments, right? The specific values of the assignments from the domain, right? Okay, so both of those can be adjusted to make this search better as you go with heuristics. Heuristics as in choices we make, not heuristics as in the formal definition previously, right? Okay, we'll talk about those later. So let's look at how backtracking works in this example. So we do blue, right? Already we're different. DFS would have assigned this blue, but blue's not an option, right? So it picks red. And then we continue. Blue is again an option there, right? So we can assign blue. And on we go. We have a problem now, right? The successor for this green node, assuming we're assigning this variable here, there are no successors. There's no valid successors, right? Because the constraint structure is graph. That node cannot be any of the 3 colors now. So we're going to back up the tree, right? That is conceptually in our search tree a leaf node, right? It's one that doesn't solve the problem, so we keep going. Make sense? Backtrack. Okay, so we remove that one. What's left in its domain? Nothing, right? Green was the only option there. So what do? Well, we keep backtracking. So we remove our red assignment there, and then we assign it green. However, green, it flashed really quickly, but green had the same problem here with this middle node, right? So it's no good. So we're going to continue back. And we're going to go backtracking as we discover the problems. And then we solve it, right? That looked a lot better than DFS did, didn't it? Okay, good. So there's kind of 3 ideas in this concept that we're going to play with in backtracking that are going to give us huge gains in execution speed. And so the first I've already mentioned is ordering. Which variables should we assign next? In what order should its values be tried? We're going to play with these near the end of the lecture. The second is filtering. Can we detect inevitable failure early? We've kind of started that process, right? But there's better ways to do that. We're going to talk about that next. Then there's also structure, which I hinted at the beginning, which is can we exploit some graph structure properties of our constraint graph in order to speed this process up. And we'll talk about that, I believe, probably on Thursday. Okay, so let's talk about the second one of these, filtering. So the first idea is forward checking. So this is the first kind of filtering we're going to talk about. And basically, what we're going to do is we're going to keep track of domains for unassigned variables and cross off bad options, right? So we're going to cross out values that violate a constraint when they're added to the existing assignment. Okay, so how's this going to work? Well, if we assign Western Australia to red, then we know that the Northern Territories can't be red and South Australia can't be red, right? So we make this assignment, we look at the constraints adjacent to the value we just assigned, right? And we remove things from the domain of states adjacent to us in the constraint graph that would violate this constraint, right? Awesome. Then maybe because of our arbitrary ordering, we then assign V here the value of green. We do the same thing. All the constraints associated with V have their domains reduced according to the constraints, and we continue. Right? Then maybe we assign, sorry, that was Queensland, wasn't it? I said V, but what's V, Victoria? Yeah, Victoria. Awesome. Sorry if there are Australians in here and I'm ruining the geography of the country. So then we assign V, right? Well, we had a problem already here, right? What's the problem here? Yes?
SA and NT only have one available value and they're next to each other.
Right. Yeah, so we as people smarter than this algorithm can identify that there's a problem already, right? But because neither of these, we're not checking unassigned constraints yet, right? We don't see it yet. So we'll get to that in a minute. But then we assign V to blue. We look at the constraints associated with V, right? And that removes blue from SA. We now have an empty domain. An empty domain is when we know that this is not going to work, right? There's no possible assignment for SA. Our current partial assignment is broken, right? Okay, this is called forward checking. So let's see how this works and how it differs from our previous example. All right, so same graph, right? But now we're going to keep track of what the possible domain is for each state. So we assign the first one blue, and what's happened? We removed blue from the nodes adjacent in the constraint graph to blue, right? How is this different from what we just did, which is regular backtracking? Yes?
We only check for the one going down versus all of the adjacent ones.
Exactly. Yeah, so in the last one, if we had drawn these colors on here, We would have taken blue out here, conceptually, depending on when you're doing that checking, right? Maybe when we talked about whatever. But we wouldn't have modified these at all, right? So that's the difference here. Right? Okay. So let's continue. We're going to assign a value here, that's red. Now what's happening? Well, the nodes adjacent to red have their domains restricted based on the constraints, right? And we continue. We already see a problem, but it doesn't. Continues. Discovers the same problem that backtracking had discovered, right? It's going to go backwards. Kind of in the same order that it did last time, right? And eventually, we're going to solve the problem. So forward checking, I'm trying to pause it in such a way it's not blank, it's flashing to say we won. But forward checking is a better filtering than what's going on with just backtracking. In fact, it is filtering, whereas it wasn't conceptually filtering before. But it's not that good, right? It's just kind of looking at things adjacent. That's almost the same, yes?
So in the case when it showed both the adjacent ones only had green, it's not aware of that at that point yet until it gets to.
Right, so it's just looking for empty domains, right? And it's only restricting domains on things that have been assigned, on things adjacent to things that have been assigned, right? Neither of those green values, those are just possible assignments, right? The domain's one, right? Conceptually, you could think of them as assigned, right? But they're not, according to the algorithm, right? But that's kind of, we're going to look at that here in a minute. Okay. So, forward checking propagates this information from assigned to unassigned variables, but it doesn't provide early detection for all failures, right? This is the case that we saw here, where NT and SA, we know that there's a constraint between them. We know there's no possible way, considering this partial assignment, that that's going to work out. But forward checking doesn't detect this. So we're going to add some notion of constraint propagation. This is where we're going to reason from constraint to constraint. And to do so, we have to kind of introduce some terminology. So we're going to introduce something called an arc, okay? And an arc is a directed edge between two states. So it's not a constraint, right, which is an undirected edge. It is a directed edge, and it exists between all of the states, right? Okay, so an arc is called consistent if and only if, for every x in the tail, that's the source, there is some y in the head, that's the destination, which could be assigned without violating the constraint. Okay, so if we look at the arc from NT to WA here, what we need to do is check every x in the tail, right? So that's every possible assignment in the tail being the part that doesn't have the arrowhead on it, right? So we say, is there some y in the head which could be assigned without violating a constraint? So is this consistent, this arc? Who says yes? Who says no? Who wants to explain why not? Yes?
Because there's no assignment you could make if you pick red.
That's correct. If you pick red in the tail, here, then there's no assignment in the head that won't violate the constraint, right? But we can make this consistent, right? We could cross that out, right? Okay, so then this introduces an important notion. There's something is or is not consistent, right? An arc is or is not consistent, or an entire graph can be arc consistent, in which every arc is consistent or is not. But then you can also make arcs consistent, right? And so we're going to look at algorithms that make arcs consistent, but consistency is a property, right? Okay, so maybe we cross that out. Is this arc now consistent? It is, right? And why? Well, because if we assign NT green, then there is an assignment left for WA that works, that's red, right? If we assign NT to blue, there is an assignment for WA, that's red, right? This is consistent. Okay. How about from Q to WA? Is this consistent? Who says no? Who says it's inconsistent? Who says it is consistent? Why is it consistent? They don't share any constraints. That's exactly right. So this highlights the difference, right, between an arc and a constraint. These exist between all pairs of nodes. Has nothing to do with the constraints necessarily, right? Although consistency between these is a function of the constraint, right? So if we pick red for Q here, what's the value in WA that works? It's red because there's no constraint, right? Okay. So it's important to remember that we're taking things when we make them consistent from the tail. We're not modifying the head, right? And so this drawing here is supposed to help you remember that, in which you're removing illegal things from the trunk when you get pulled over by the arc consistency police, right? Okay. Take things from the tail. Delete from the tail. That's really important. It's going to be on a bunch of slides. I'll try to remind you frequently. Okay. So forward checking enforces consistency of arcs that are pointing to each new assignment, right? That's, conceptually speaking, what forward checking was doing when we talk about this notion of arc consistency, right? It was enforcing consistency of arcs that point to the assignment. But we can look at arcs that aren't assigned between two states, or two variables that aren't assigned, right? So the other end of the spectrum would be, let's make all arcs consistent all the time, right? Okay, so this is arc consistency of an entire CSP. So this is a conceptually simple form of propagation. You make sure all arcs are consistent. Okay? Remember, delete from the tail. That's important. Okay, so let's look at this. So let's look at the arc from V to NSW. Is this consistent? Who says yes? Who says no? It is. For any value at the tail, red, what would we want from NSW if we pick red? Blue works, right? If we pick green, either works. If we pick blue, then we can pick red, right? Consistent. Okay. What about from SA to NSW? Is that consistent? It is, right? Because for everything in the tail, there is something in the head. That's important, right? So for everything in the tail that's blue, what's the thing that works at the head? Red, right? Okay. But now it's going to get interesting. Is that consistent? It's not, right? And why is it not? Because if we pick blue, then we're out of options, right? And so what should we do? Yeah, let's leave blue. Right? Goodbye. Now is it consistent? Okay, cool. Yes?
Would it also be consistent if you added like green?
To the tail?
Well, to the head.
Yeah, I guess if we started adding things to the head.
I know, but like just.
But there's a reason that they're not in the head anymore.
Yeah.
Right? Because they're violating
Because
the
that would
constraints.
violate those, yeah.
Yeah. So, I guess maybe in
Sure,
some
yeah, but
possible
delete from the
algorithm
tail.
we're going to start messing with what's adding things to the head, but let's not.
Yeah,
For now.
sure.
Okay. So this is now consistent, but there's a problem. We've introduced a problem. What's that problem? Does anybody see it? What's that?
It's no longer consistent with V.
That's right. We already checked V to NSW, right? We said that's great. It's consistent. We're done with that arc, but it's no longer consistent. So we're going to have to recheck it. That's kind of a bummer, right? Is it consistent? It's not. Why is it not? Because red won't work with red, right? So what do we do now? Right? Is it consistent now? That's great. Okay. This highlights a really important point, right? If x loses a value, all neighbors of x have to be rechecked. Okay, so what's the arc we're looking at now? SA to NT. This is the arc that was, this is the set of variables, the constraint that was causing us all the problems, right? If we're checking all the arcs, are we going to detect this early? Well, what happens now? So let's say we're checking SA to NT, ignore the text that came up. Is it consistent? Okay, it's not, so what do? We take out the thing from the tail, right? What do we have? An empty domain. the algorithm says, whoa, that's no good, right? Backtrack. Which is built again on vector search, right? This is all kind of a subroutine that's kind of encompassed in a DFF. Okay. So our consistency will detect failures earlier than forward checking, much earlier, right? We can run this before we make assignments or after we make assignments. Those look kind of similar. Generally, we do it after. Okay, what's the downside? Yes?
Seems like it's a little bit more of an expensive check.
It is expensive, yeah, maybe, right? So, you know, we have to check all of these arcs, right? If we're smart, we restrict it by the constraints, so we're not doing pairwise stuff, but we still have to check a bunch, potentially. And then what happens when we start modifying them? Well, the ones we checked are not good anymore, right? So we have to then recheck those things, and recheck those, and then recheck those, and potentially, are we going forever?
Maybe if it's not a solvable case.
So it's something to be worried about, right? When you start looking at rechecking things that you've already done, redoing work, is this going to converge? Is it ever going to stop? It will, under reasonable assumptions, like finite domains and things like this. But yes.
Yeah, it just seems like our consistency could also almost be turned into its own search problem.
Yes. Yeah, that's a great point. So there's this notion of, we saw this in A-star, right? How expensive is the thing you're using to make your search faster compared with how fast is your search if you didn't use it, right? It's an important balance to play. So returning to the previous point, it will terminate. Does anybody know why? Yes?
There's only so many values you can delete.
Yeah, you're deleting, right? So you can only add the neighbors back into your data structure d times per node, right? Does that make sense? Because you're never adding stuff to the tail, right? Okay, cool. But that's important to think about, right? Okay, so computation time. So here's the pseudocode for our consistency. I'm not going to go through it in detail. You should. But generally what we want to talk about is the runtime, right? And so for n variables, d is the cardinality of the domain. This will run in n squared d cubed. But if you're smart, with some tricks, you can get it down to n squared d squared. Okay, that's way faster than d to the n, right? Okay, so there is a question, is this worth it? Is this computation worth it? The answer is usually. Now these are NP-hard problems, right? So you can't say it works every time, right? That's the problem. But almost always this is going to work really well. Or it's going to be worth the computation. Not necessarily, it's actually going to work really well, but you first.
So this function, these two functions are thrown into the backtracking
Yes.
search function.
So this is happening after every variable assignment in that order. Yes?
That being said, I feel like you, especially looking at the constraint graph that we're working on with this problem, there's simpler ways to solve it than doing hard consistency quickly, like always doing checks to fill in the, like you could have a cost associated with nodes that have less domains available, and you could fill those in first, and that would eliminate more inconsistent branches of like DFS.
Great point. Yeah, so what's one of the things that we can change that I highlighted on our slide earlier? It's the ordering, both of the nodes that we pick, the variables we pick to assign at any given step, and the value we assign them from their remaining domain. So what you're describing is messing with that ordering, which is generally a good idea. Yes?
Would that also kind of play into like preferences, where we would kind of prefer like, the first node to be this way, but if there is literally no one, then it has to like go through another branch?
Yeah, so very good point. I don't want to get too deep into how you change this into an opposition problem where you have preferences, because there's a whole can of worms to be opened there. But yes, you can kind of look at these notions of ordering, changing your ordering in order to discover preferable solutions early. Yeah, definitely.
So, would you prefer finding like an optimal ordering before exploring like a more expensive search algorithm?
So, finding and ordering, or
would you, I mean like if we were looking for, like we take a more naive DFS just apply like what we think of as an intelligent order into its search problem, is that typically preferable because it's less expensive?
You should do both. Really. So, it's an exponential space. In the worst case, use all of the tricks you can. We'll talk more about ordering here in a minute. Okay, so what are the limitations of our consistency? So what can happen after we enforce consistency? We can have one solution left, right? If every variable has only one possible assignment in the domain and those all happen to work, then we have one solution, right? We have multiple solutions left, as is the case with this upper right graph here, right? Either of those can take on either value, but they can't take on the same value, right? But our consistency doesn't know that. But we can also have no solutions left and not know it, like this lower right one, right? There is no solution from the available domain to this lower right graph, because as soon as we assign a value to any of these, it breaks the whole thing, right? But our consistency won't know that until we assign a value to those, right? And that's because there's this notion of kind of a three-way situation here, right? It's not encoded in we'll check. Does that make sense? Awesome. Well, let's see how our consistency is going to work in kind of that same search video we were looking at before. But yes, this is an important note. Our consistency works inside backtracking, as we discussed. Right? Okay, so let's see how it works. We're going to make the graph bigger. All right, so it's more interesting. We've already kind of got the machinery that we solved that easier search problem easily, so let's look at something a little more complicated. Okay, let's see what happens. Okay, so we've assigned one value, and we've made the entire thing arc consistent. And what happened? It's not very interesting, right? All we did is we removed adjacent nodes, a single value from their domain, right? That would have worked in our forward check. That's exactly how forward checking would work, right? But that's just because there's no implication of that yet further down the stream, right? So then let's pick one more value here. And now let's look at what happened. Okay, so this has one neighbor that's not assigned, right? That's this one here. That looks like just what it would have looked like in forward checking, right? But there's something else going on here. Its neighbor has had its domain restricted now, right? Because there's only one choice here. We haven't assigned it, right? But this notion of our consistency has enforced that its neighbor has to be consistent now, right? Okay? Both of its neighbors, right? There's two. Okay, so now we're going to assign another variable, again highlighting the difference between, yes, pointing out that there's nothing there. Then eventually we're going to assign another variable. Oh no. All right, hold on, I'll figure this out. Okay, let's just pretend we haven't seen this before. I'll work on the technology for next time. But we assign this. It has implications further down the graph, right? In fact, we've checked the whole graph for our consistency. That has modified domains and variables that are not adjacent to assigned values. We continue down, we start to see this complex propagation going on, right? So nodes that are 1 removed, 2 removed even, n removed from assigned values have had their domains restricted, right? Okay, then we continue. Is it just going to work? No, not necessarily. But with backtracking, we find a solution, right? Okay, so this is an example of very complex filtering. Let's take 5 minutes. Great. Okay. Come back. Now we're going to start talking about ordering. separate some formalization, that kind of stuff. Kind of get a free-form answer. Projects are going to be all about so implement this kind of solution for this specific problem. So project 0, no partners, project 1 will.
Kind of piggybacking on that, so are most of the other projects going to be still on top of each other? Or
generally speaking, there's going to be kind of a theme of progression in which you're going to be making more complex happening. It's not going to be exactly.
but most of them will be part of it.
All of them, as of now, other than the one due, is not.
Okay.
keep meaning to give you this 5-minute break like in the middle of class and not 15 minutes before putting the class. But I'm so excited about artificial intelligence that I forget, which is only partially a joke. I actually find all this super exciting. But like, help me remember. If it gets to be the middle of the class, and just say, hey, could we take a break and we will, right? Sound good? Okay. Because we're also like very, very close to the end of the lecture, so it didn't really make much sense to take a break here, but we did anyway. Okay. Ordering, right? This is one of those things that we can kind of sliders and turn knobs to make our algorithms work a little better, right? And the two things that we're changing are the orders in which we assign variables and the orders in which we try assignments from those variables domain, right? So let's talk about the first, the order in which we assign variables. We're going to call this minimum remaining values. So the idea is that we're going to choose the variable to assign next with the fewest legal values left in its domain. This is taking the hard road, right? Why would we want to pick the one with the fewest values and not, say, the one with the most values? Yes?
You might find an optimal solution faster in that configuration over like trying multiple, like where the domain has more value.
So let's be really careful about optimal. So we're not really considering costs or values associated with solutions, right? We just want solutions. But there are things at play here when we start talking about optimization of these algorithms as well, for sure. Who has another idea? I think I saw your hand first.
So with this, you would fail really early by assigning these values as soon as possible.
Exactly. So the intuition here is that we have to assign a value to every variable eventually, right? And if our current partial assignment is bad for reasons that we can't see yet, we want to learn that earlier rather than later, right? Because we're going to do a bunch of unnecessary computation to learn that if we don't, right? So the earlier we can identify a partial assignment is not going to work, the better. And the intuition here is that problem areas are going to be in regions with restricted domains, right? Does that make sense? Again, does this work always? No. Are there worst cases for everything? Yes. But this is kind of the intuition, right? It's heuristic. Okay, so we want to fail early. So if we pick red here, then we should be assigning values adjacent to that because those values have had their domains restricted, right? And so on and so on. So we talked about why min rather than max. This is taking the hard road. The intuition is we have to assign every variable at least once. So, okay, this is also called fail fast ordering. So when you said it fails fast, that's very intuitive. It does, and that's what we want. We want to fail early, right? Okay. We also saw this problem in DFS where we had to backtrack like functionally forever in order to fix the problem that we identified very deep, right? That's not a problem that's necessarily unique to DFS. We haven't solved that problem necessarily. There are cases where we create a problem with the first or second assignment, depending on the constraints, and we don't discover it even to the best of our abilities until really, really far down our search tree, and because of the way backtracking works, it's going to take forever to figure that out, right? Not forever, but a long time. So this notion allows us to kind of retain some notion of locality in our search tree so that our backtracking kind of stays local, right? Does that make sense? It's all kind of an intuitive idea. But okay. So let's look at how this works. Okay. So now we're going to pick one with the least number of remaining elements in its domain, right? That's one of these two adjacent to that one. I think it's going to pick the lower right one. Yes. Right. And previously, we had picked the one next to it, right? Because we had some functionally arbitrary ordering that we were following. But now We're gonna pick one with the most restricted domain, that's gonna be up there, right? So eventually we do so. Eventually. Okay, now we have two choices. There's some tie breaking right that has to happen, but we're gonna pick one of the two. We're gonna assign a value to say that one. Right, and continue on. Picking the most restricted one. So we had problems that manifested up here earlier, right? Because of our choices here that we didn't discover until we had gotten really deep, right? And if you remember the backtracking, even in our best searches that we've done, the backtracking took a little bit because the problem manifested early, but we didn't find it until later. Right? This allows you to find those problems conceptually speaking earlier. Okay, we're going to take the opposite approach when we assign our values from the domain. So this is value ordering. We call it least constraining value. So given a choice of a variable, we're going to choose the least constraining value. So again, we've already picked our variable we're assigning, right? That we picked by the hardest one. Now we're going to pick from the domain the one that rolls out the fewest values in the remaining variables. Why would we want to take the opposite approach here? Intuition, yes.
It leaves as many options available for the future.
Yeah. So kind of continuing, exactly. So continuing on kind of the same intuitive thread that we were pulling on earlier, we have to assign a value to every variable. We might as well get the hard part out of the way early there. We don't have to investigate every possible assignment, right? So in this case, where there's no cost or notion of optimization, like you two were talking about earlier, we just pick the one that seems like it's going to be the least restrictive as we go. In this way, maybe we'll have to check fewer possible assignments. Right, that's the intuition. That's what makes it different from the hard road choice that we made earlier, right? Does that make sense? Okay, so to summarize then, in our ordering here, we're going to pick variables such that we fail early. We're going to pick from the domain such that it produces the least restriction. And that's going to be how we order these two things. That's kind of the conceptual way to do it when you don't have other reasons, problem specifically, to choose different ways to choose them. Right. Does that make sense? Okay. I'm going to stop there. We're going to cover some more details on CSPs on Thursday, and we'll go from there. Sound good? Oh, sorry. All of these ideas together can make you allow you to easily solve an NP that's like 1,000.
Do we have any assignments to do?